Hi guys, and welcome back to PHILIPTRONIKS Repair Solutions, and I especially thank you all of you guys for subscribing to our channel. And recently we got 1K subscribers, and it's because of you guys, so thank you so much. And stay tuned with our channel, and we will be posting more informative videos in the near future. And so today we got this laptop for repair. So the problem with this laptop, it is working fine, but if we press the power button, it doesn't respond to the power button. So it's similar to the case that we posted before, which has the problem like occasional shutdown or occasional no power case. That is also an ASUS laptop, and this is also an ASUS laptop. So the problem with this laptop, so if you connect the adapter, the board will be working fine, there's no problem. But if you try to shut down the laptop and try to press the power button, it won't respond to the power button. So after that, you need to remove the battery and remove the adapter, and then you need to connect the adapter, and automatically it will start. If the board starts, it will be working fine. But if you press the power button, it won't respond to the power button. So this is the case in this laptop. So let's diagnose the motherboard and see what is the problem in this laptop and which sections are causing this problem. So let's see whether we can fix this one. Okay, so now let me connect the adapter. So I should see that the board should be turning on automatically. Okay, yes, it's connected. And you can see the ampere reading is 700 milliamps and the board has turned on. Yes, we got the display, so there's no problem with the display. Yes, and the board is working fine, there's no problem. So we need to shut down the laptop. So watch out the ampere reading. So we should carefully watch the ampere reading when the board turns off. So in that ampere reading only, we are going to decide what's the problem in this laptop. So actually when I received this laptop, I just had a look about what could be the problem, because it looks like a peculiar case because I never attempted this type of case. So the laptop is not responding for the power button. So this type of case is actually a different one. But I have just went through before and just got an idea. So I just watched the ampere reading on the DC power supply, and then I decided that, okay, I'll show you how I found it. So yeah, so it's working fine. So let me shut down the laptop. Okay. So just watch the DC power supply when the laptop turns off. So I'm really interested in sharing this case with you guys. So this will be a unique one. Okay, now the laptop is going to shut down. Yes, now the laptop has shut down. And if you look at the ampere reading, it's now at 14 milliamps. Okay, now let me press the power button. So I'm pressing the power button. No response. There is no reading, no change in the ampere reading right now. So it's at 13 milliamps and it is stuck at 13 milliamps. Yes. And if I disconnect the adapter, okay, the adapter is disconnected. And if I connect again, then it will automatically start turning on. Yes. Now you can see the ampere is taking around 700 milliamps and the board has turned on. There's no problem. So I did a couple of times, more than a couple of times, like 5 times. So if I press the power button and shut down, so the board is occasionally going at standby ampere like 30 milliamps. So if the board is at 30 milliamps, if I press the power button, then the board is starting on. But if the ampere is stuck at 14 milliamps, the board is not starting. So what I was guessing is that there is some problem on the power sections on the standby. So some of the voltages has not been produced. So that's the problem. So I'll just show you this. Okay, now let me press the power button and shut down. Okay, so now if you look at the ampere reading, it's at approximately at 30 milliamps. And now if I press the power button and it will start. Okay, now I'm going to press the power button. Yes, now the board is working. And the board has turned on, so you can see. Yes. So let me shut down again. Yes, now it went to 14 milliamps again in the previous stage. So what I did was, so I checked the voltages at the standby when the ampere reading is at 14 or 13 milliamps, and then I checked the voltages when the during the standby when the ampere reading was 30 milliamps. So I just found a clue there. So we are going to focus on that and try to repair this motherboard. So I have just removed the back cover here, so you can see this one. Okay. Yes. I'll just open half, then only we can press the power button. Okay. So you can look at the coils. So we need to check the voltage on the coils. Right. So if you check now, the ampere reading is at 13 milliamps. Okay. Okay, let me check the voltages. So on this coil, yes, we have 3.3 volt. 3.3 volt. And on this coil here, we have 12 volt. Okay. And this coil, yes, we have 5.3 volt. And on this coil, we don't have any voltage. Okay. This may be the GP coil, so we may not have this voltage right now. It's a run per voltage. All right. So on this coil here, we don't have anything. And on this coil here, we don't have anything. Okay. So we have checked entire coil. So we have only the voltage on these three coils. So one is 3 volt, 5 volt, and 12 volt. Except these three coils, we don't have any voltage on any other coils. So what we are going to do now, we are going to turn on the board again and try to get the ampere reading around 30 milliamps, and again we are going to check the coil readings. Then we can get a clue here. So that's how I found this problem. Okay, so I'll show you guys. So let us turn on the motherboard. Okay, the adapter is disconnected. Let me connect again. Yes, the board is turning on. Now let me press the power button and shut down. So yes, so now if you look at the ampere reading, now it is at 30 milliamps. So let us turn around the board and check it and check the voltages. Okay, again. Okay, on this coil we have 3.3 volt. Okay, on this coil we have 5.3 volt. Okay, on this coil 12 volt. Okay, we don't have any voltage here. Here we should not have any voltage here. And on this voltage, on this coil we have no voltage, and on this coil we have 1.1 voltage. So if you look at the ampere reading, so now we are having 30 milliamps and we are getting a voltage on this coil. But if you can remember, before we don't have a voltage on this point here, and the ampere reading was 15 milliamps. So now the extra 15 milliamps is because of this voltage is being produced in this motherboard. So that's why we are reading 30 milliamps right now. So if I press the power button now, it should turn on. So let me press the power button. I'll show you. Okay. I'll press the power button. Yes, now the board is turning on. No problem. And we are getting the display. Okay. So basically, there's a problem with the standby sections. So if a voltage was not produced, then it will send a power good bad to the SIO, then the SIO won't send any other signals if those power goods are bad. So now we are going to check the problem which is causing for this 1.1 volt to not to produce. So this is a problem here in this motherboard. So let us check. So anyhow, we need the schematics. So I'll try to find the schematics for this motherboard and see whether we can go through that and find a solutions for this one. I hope we can fix it. Let's see. Okay. Okay, so now the board is out. So we can check this one and the board looks fine. There's no problem in this motherboard here. So what's in here? Okay, so it's a RAM slot. So if we want, we can fix an external RAM here. So we have an onboard RAM also here. So no problem. So it's a good laptop. Actually, we having a GPU also in this motherboard. Okay. All right. So let us try to find the schematics for this motherboard. So first we can study the schematics and we can start accordingly and follow the schematics and try to find a solution for this motherboard here. Okay. Okay, so we couldn't find the schematics for this motherboard. So basically ASUS laptops mostly doesn't have schematics. On some cases we might find some schematics for ASUS laptops, and on most cases you might find these types of repair guide, like a repair guide for those motherboards. So you can see it is K501LX. So the model number is same and the part number is same as it is on the motherboard here with us. So it's K501LX. So it is relevant for the schematics, and this repair guide is relevant for the board that we have right now. So okay, so this is not similar, like it is not equal to the schematics, but we have some important informations in this repair guide, so we can use this one. So rather than not having anything with us, so it is better and it might help us in troubleshooting the problem with this motherboard. Okay, so first here we have the timing sequence, the power on sequence of this motherboard. Okay, so the first voltage in this motherboard is created by this IC, so which is a standby IC, and then it will release the power for the EC chip here. So this is the first sequence in the power, and on the second sequence we have the EC reset signal that is sent to the EC chip to reset the power management sections of the EC. Once after the EC being reset, then it will start to function its power management and also its IO pins according to its configuration. So in this motherboard we are having a problem that occasionally 1.05 volt is not generated. So if we shut down the laptop using the Windows, then it won't boot up if you press the power button. So this is the problem with this motherboard. But if you connect an adapter, and it will automatically turn on and it will be working fine. But if we press the power button, it won't respond to the power button. So this is a problem actually in this motherboard. So we can use these timing sequences in order to identify where would be the problem in this motherboard. So basically here we have an extended version of the time sequence as a timing line, so we can find each of the signals. So here we have 1.05 volts, yeah, it's here. So this is after the S4 and S3 signals. So you can see this is another name for S4 and S3 signal you might find on some schematics here. So sus C has is equal to S4 signals and sus B has is equal to S3 signal, and this is the signal that comes first and this is the signal that comes second. So you can see the timing. So approximately it should be greater than 30 microseconds. So if S4 signals is released after at least 30 microseconds only, S3 signal should be released. So S4 signal is sent to the RAM regulator in order to regulate the RAM voltage, and also S3 signal is sent to all the run power voltages. So it's like 1.05 volt, it's like PCH power, and also the CPU voltages, and also all the load switches, and everything activates when the S3 signals comes there. Okay, so actually we were having 1.05 volt at the always stage in our motherboard, because we were checking that when the board is turned off we had the 3.3 volt power here, this voltage 3.3 volt and 5 volt, and also 1.05 volt as well. But according to the timing diagram, so they are mentioning that this voltage should be generated only after the S4 and S3 signals. So here we have some discrepancies with the guide and also actual condition in this motherboard. So anyhow we can confirm it, like, so we have a best friend with us, so he will say which signal comes one after the other. So that is the oscilloscope. So here we have an oscilloscope with us, so it's a 2-channel oscilloscope. So we are going to probe one of the probe in 5 volt output, or like 3 volt output line, one probe, and also the other probe on the 1.05 volt output line. So we need to place on the coils or on any of the output lines. And if we check the reading, so we might find the time gap between these two voltages. So we need to find these two voltages, and if we have a low time gap between these two voltages, we can confirm that this voltage 1.05 volt is generated before the S4 and S3 signal. And also we can confirm it with, first we need to check, the first point is to check with the 3.3 volt and also 1.05 volt, and we need to take note of the time difference between these two signals, and then we can go with the 1.5 volt, which is the RAM power supply, and we need to again consider the difference between these two voltage. So if we have a highest difference on these two voltage, we can confirm that this is generated before this one. But actually according to the schematics, they are saying that 1.05 volt is generated before 1.5 volt, but we need to make sure this voltage is generated before these two signals, because now actually in the motherboard we were checking that before pressing the power button we had 1.05 volt and also this 3.3 volt and 5 volt. So we need to make sure this signal output, but actually we can't find a place because we don't have a schematic, so we don't know how to find a place where we can find this signal output. So it is better to find this signal and also this voltage. So we need to compare which comes first with respect to this 3.3 volt. So we can compare first the 3.3 volt with this one, I mean the 1.05 volt, and then we can compare 3.3 volt with the SUSC has signal, and we need to compare it. So whichever the time difference is highest will come the latest, and whichever the time difference is the shortest will come earlier. So on that case we can find whether it is before or after pressing the power button, or on other words we can say it is before the S4 and S3 signals. Okay, right. And also, so you can see this is the 1.05 volt output coil, and here we have the 3.3 volt output coil here. So I'll make it a little darker so it's not visible here, the pencil lines. Alright, yes, so this is 3.3 volt here, the coil, and also here we have the 1.05 volt. So when the ampere was reading around 0.30, we had this voltage there, although the CPU voltage, RAM voltage was absent there. So on that case we can make sure that S4 and S3 signal was not present. So if the S4 and S3 signal was present, we might get this RAM voltage and also the CPU voltage as well when this voltage was produced. So actually we can see here the signal 21 says 1.05 volt VS power good. So it's VS power good means it's a run power good. But actually we are getting this voltage at the always state in this motherboard. Because if you don't get the voltage in this motherboard, the board is not turning on if you press the power button. So that's a problem here. So it doesn't matter if it is generating before or after pressing power button, it doesn't matter. But if you don't get a voltage on this coil, the board is not turning on. So that is the problem here. So that's why we came into this section in order to see actually it is generating before or after the pressing the power button. So according to their timing diagram, so it is generated after the power button because now the signal is here at 21. So we need to go down to 20 and 19 to see what are the signals being generated on that section. Okay, so here we have a nice signal, so which is SUS_B_EC. So which means this signal is sent by the EC chip, right? So this SUS_B has is equal to the S3 signal. This is sent by the EC chip. Once the EC chip receives the SUS_B has signal, the S3 signal from the PCH. So once it receives the S3 signal from the PCH, then the EC chip will send the SUS_B_EC to the RAM regulator in order to generate the RAM voltage. So we can find a place where the PCH send the SUS_B has signal. So it's here. We have, it's on 17. You can see PM. So PM means is the property of the PCH, the power management. So this is the signal that is sent from the power management of the PCH. We can see it on this point here. So that is the SUS_B has signal. So we can check on this point. And if we go down to the signal 16, the timeline 16, we can find the S4 signal that is needed to be generated to produce the RAM voltage. Yes, so it's power button. Yes, here we have the pin number 16, the signal 16 that is sent from the power management to the EC chip as an input to the EC chip as SUS_C has, which is equal to S4 signal in order to generate those voltage. So no problem. So what are we going to do now? We'll just leave it as it is, and we are going to test with our oscilloscope with our two channels that we have here. So one channel on this point, which is 1.05 volt, and the other channel on this line, which is 3.3 volt. And we need to take a note of the timing difference between these two. Okay, so as a good measure, first we can check on these things. So as a first checkpoint, we can check on 1.05 volt. So on 1.05 volt between 3.3 volt. So this is the first checkpoint, and the second checkpoint we can check 3.3 volt and then to 1.35 volt RAM power supply. So this will be a first checkpoint. After that we need to check with regard to S4 signal. So we can find on pin number 18. So here we have a 6-leg IC on the middle pin here. So on middle pin here we have the S4 signal from the EC chip. So we can compare this signal with the output of 1.05 volt and also 1.35 volt. So the second checkpoint is S4 signal with 1.05 volt an S4 signal with 1.35 volt. So we should have a highest reading, highest reading on this point if we confirm that this voltage is generated after this voltage, which is 1.35 volt. But if we have a less time difference between these 2 points compared to this one here, we can confirm that 1.05 volt is generated before 1.35 volt. So on that case, I can confirm that this is generated at the S5 state or somewhere between S5 to S4. So in our case here in this motherboard, so we are seeing a voltage on the standby, that is 1.05 volt is present on the standby. So we should get a lesser reading between S4 and 1.05 volt, and we should get a higher reading, the timing difference, we should get a higher timing difference between S4 and 1.35 volt. So we need to compare this one. So based on these things, we can conclude that which are the signals and voltage comes one after the other. So we are dealing with this one in order to bypass a signal, because 1.05 volt is occasionally not being produced. So some signal is not sent to the regulator IC, I think. So we can check the regulator sections as well, the 1.05 volt regulator sections, and we can confirm whether we have the enable signal and also the power good output from this regulator is okay. So we can first check on the motherboard and let's take a decision what to do with this 1.05 volt. So actually we don't have a problem on the regulator, because if we connect the adapter, automatically it is turning on and the 1.05 volt is generated perfectly and we are getting a display and everything is working fine. But if you press the power button, only this voltage is not generated. So there is a problem on some of the signals. So maybe the EC chip may have an internal problem occasionally where it may not send an enable signal to this regulator here. So we need to find that. So accordingly we can check according to the first sequence and also the second sequence here, and we can conclude which signals comes one after the other. So let's move on to the oscilloscope and have a check on the motherboard. Okay, so now the oscilloscope is visible to you now. So we have only one camera for external record, so we can record only one device at once. So now we don't need a power supply, so we can just record only the oscilloscope here. So we have two channels in this oscilloscope. So we are using Handtech 100 MHz oscilloscope here. So here we have a yellow channel which is directly connected to the 1.05 volt output. So I used a jumper wire here and connected to this probe here in order to sense the voltage and the rising edge of the voltage. And I can use the other probe, the green channel, in order to probe on the output of the 3.3 volt. And if I trigger the power button, if I connect the adapter, I can get a voltage reading on the oscilloscope. But we need to set the oscilloscope to single sequence function, then only it will capture the rising edge of the both voltages. Then we can find which voltage is coming first and which is coming in the second. So let me shift to single sequence mode. Okay, now it is set to single sequence mode. So let me probe the other probe here on 3.3 volt. Now watch of the display of the oscilloscope. Right, I am connecting now. Yes. So if you carefully look at the display of the oscilloscope, we can see the yellow channel, which is 1.05 volt, and green channel, that is 3.3 volt. So we need to study that signals here. So let me bring it at the center so it will be easy for us to see it. Okay, and let me zoom a little bit. Yes, so we can use the cursor function in the oscilloscope in order to see the voltage, the timing difference between the voltage. Okay, so if you look at these two lines here, so you can see once the adapter is connected, both of the voltages are rising, and after some time you can see that both of the voltages are falling. So this is because once a BIOS inside the EC chip is read, then the BIOS will configure the GPIO pins of the EC chip, and then the GPIO pins will low all of these signals down. But however, once the adapter is connected and the power button signal and also the S4 and S3 signal is released from the PCH, then it will pull them or pull both signals high, the voltage is high. So at that time you can see the first green channel, the second green channel is pulling first to high, and then after some time only the yellow channel is pulling back to high. So this is the time gap between both of the voltages. So we can check that using the cursor function here. So let me take it. So we need to start from this point here. So the rising edge is at this point. So we can check from this point here. Okay. Yes, at this point. So you can see the reading on this side here, Bx minus Ax, which is 116 milliseconds. So once 3.3 volt voltage is produced, after 116 milliseconds only 1.05 volt is produced. So this is the implication of this reading here. Alright, so we can take a note of that. So the time difference between 3.3 volt and 1.05 volt is 116 milliseconds, and also the 3.3 volt only comes first, then 1.05 volt comes second. Now let's read 3.3 volt and also the RAM voltage, so then we can see whether we have the time difference greater or lesser than this 116 milliseconds. Okay, so now we can check 1.5 volt and 3.3 volt and check which signals or which voltage comes first and second, and compare with the result that we got before with 3.3 volt and 1.05 volt. So I'll explain to you very clearly. So first we will just record the reading here, so I can use with my hands together. So this is 1.05 volt, so I'm probing yellow channel in 1.5 volt, the RAM power voltage, and the green channel, as same before, I'm using for 3.3 volt. And again we are going to set to single secant function and connect the adapter and see what's happening there. Okay, no reading, wait a second. So yes, so I need to probe correctly, otherwise there won't be any reading. Let me capture it again. Okay, hold it. Yes, let me connect the adapter. So yeah, so we need to bring the trigger at the center, then only we can see the reading on the center. Okay, right, let me capture it again. Yes, so we can see that yellow channel is rising first still, but the green channel is not rising. Is that so? I think I have not probed the green channel correctly, I think, because green channels should rise first, because it is 3.3 volt always. So I have not probed it correctly. Yes, so you can see the yellow channel is 1.5 volt, the RAM voltage, and the green channel is 3.3 volt. So now let us check the time difference using the cursor function here. Yes, go to X. Okay, so yes, So you can see the frame is now smaller than the actual time difference, which means the timing difference between 1.5 volt and 1.05 volt is different actually. But I think this is correct because according to the timing line that we saw before on the repair guide, though, so the first signal comes, the first voltage is 1.05 volt, and only after 1.05 volt we are getting 1.5 volt according to the timeline, and we can see, and it is correct. So you can see the reading here. On this point we have 390 milliseconds time gap between this point and this point here. So we can confirm that 1.5 volt is generated after 1.05 volt. So 1.05 volt would be somewhere here on this region, because it is generated after 3.3 volt is enabled within 116 milliseconds, and only after 116 milliseconds only the 1.5 volt is produced, which is after 390 milliseconds. Okay, right, so that is fine. Okay, so the first checkpoint is finished. So we have checked 3.3 volt and also 1.05 volt. We saw that 116 milliseconds was the time difference, and we saw that only after 3.3 volt is produced we are getting 1.05 volt. And the second checkpoint we got with regard to 3.3 volt and also 1.5 volt, we saw that there was a time difference there was a time difference about 392 milliseconds from 3.3 volt and 1.5 volt. So as that we can conclude that 1.05 volt is present first and 1.5 volt is present the second time. Okay, so now we can check the voltages of 1.05 volt and also 3.3 volt from the ASUS C-hash signal on this IC here. So if you look at this IC near the battery connector, it's here, yes. So on pin number, I think, yeah, on pin number 2, yes, here on pin number 2 we have 3.3 volt, which is equal to the ASUS C-hash signal that is sent from the PCH. So we need to check whether this signal comes first or the 1.05 volt is generated first. So on that we can conclude whether the 1.05 volt is generated before the ASUS C-hash signal is present. Okay, and also it is very careful to check the voltage on the middle of the pin, because this pin is directly connected to the PCH, and as I check a voltage on this pin here, we had 14 volt. So I don't know why there was like high voltage on this pin, but if we mistakenly short this pin together, then PCH or SIO will get shorted. So we must be very, very careful with that. So for that I'm going to just connect the oscilloscope probe on this wire here, so it will be easy, so that we can use by our hand for using one probe only. So in order to hold it in a very good position to check it. Okay, right, so let us check whether the 1.05 volt is generated before ASUS C-hash signal, which is sent from the PCH. Okay, right, so for that let me connect the probe here. Yes, so I can connect the yellow channel. Yellow channel connected. Right. So and it is now set to single second function. Now channel 1, the yellow channel is for 1.05 volt and green channel now it is for 3.3 volt. SUS-C has signal. Everything is okay. Now let me connect the adapter and see the result. No, there's no reading. Wait a second, I think the ground for this probe is not appropriate. Maybe. Okay. Let me check again. Fine. Set to single second function. Okay. Let me connect the adapter now. Yes, connected. Now you can see the signal has captured. All right. So on the yellow channel we have the 1.05 volt and the green channel that is the 3.3 volt. So that is the SUS-C has signal from the PCH. So you can see here, so the yellow channel, the rising edge of yellow channel is first and then the rising edge of green channel is coming. So we can see the time difference with the cursor function here. Yes. Okay, so we have 274 milliseconds and we can confirm that 3.3 volt on the SUS-C has signal is coming after 1.05 volt. So we can make sure that 1.05 volt is present before S4 and S3 signal. So we can go to the timeline and just confirm it whether it is correct. Wait a minute. Oh wait, okay, so the signal that we tested now, so this SUS-C has signal, the S4 signal is sent from the EC chip. So EC chip takes some delays in order to send the signal after receiving from the PCH. So according to the timeline, this signal should come after 1.05 volt. After generating 1.05 volt only, this signal should come. So accordingly, we are having the same reading, which is the 1.05 volt is generated before this SUS-C has signal from the EC chip. So we need to check the S4 and S3 signals, or else the SUS-C has and SUS-B has from the PCH itself. So then only we can check whether 1.05 volt is present first or after the SUS-B has signal. So according to the timeline, the 1.05 volt is present only after the SUS-C has signal which is sent from the PCH. So here is the main point, so we need to check only this point. So this is going to help us to decide whether 1.05 volt is present before or after S4 and S3 signal. All right, so now we need to find a point where the S4 and S3 signal is straightly sent from the PCH. Okay guys, so I just wanted to show you something. So everything is visible here, so I didn't notice that before, so we did not check physically this motherboard. So because the board is working fine, there's no problem with the motherboard, so I did not go into physical inspection. So now I am able to spot some of these things here. You can see the places is little bit corroded, so some of the resistors and capacitors have been corroded, so we need to clear them all. And if I flip around the other side, we can see on the other side, on the same place, we have the EC chip. So because of the corrosion on this side, so there may be a problem on signals released from the EC chip and also signal coming into the EC chip, and they can cause the 1.0 volt not being produced if there's a problem on these lines here. So first I will just clear them all and make it as a neat lines, so then we can go and check whether the board is working fine. If you look at this point here, some of the pads are being corroded. So on this pin, on this pin here, so here was a pad and now it is corroded, and this is the point where the SASI has signal, which is the S4 signal that comes into the EC chip from the PCH on this side. And also these are some of the signals, so we need to confirm that these lines are okay first, so that we can confirm that the voltages are going to the EC chip on this line is okay. And also if you look at this point here, it looks like there was a component on this place here, so like a capacitor or maybe a resistor on this point. So the board image that we saw on the repair guide is not that much clear to see if there's any component in this place, so I can't make sure whether we have a component on this place. Okay, fine. Yes, it looks like there was a component, isn't it? Yes. So if you look at this point nearby here, so you can see nice balls. So it's like the curve here, but it looks like more flat. It looks like more flat here. So maybe there could be a component in this place. Okay. Anyhow, let me clean it and see whether we can fix this one. Okay, let us try. First let me apply some alcohol and clean it. Okay, the tracks looks fine. There's no much corrosions there, just a little bit of dust. So that looks fine. I can just tin the resistors and the pads here just to make a solid contact. Still, it looks like there was a component here actually, but I don't know it's for sure. Let me see. Yes, so now this place is now visible and it looks fine, and this is also fine. Yes, this point, yes, this is also fine. It looks like okay. Yes, so that is okay with. But there's, if you look at here, so these tracks are a little bit corroded and there's a little bit of damage on these tracks. So we need to make sure the tracks are okay. Otherwise, these types of problem can be caused due to this thing here. Okay, the multimeter is here and you can hear the buzzer sound. Yes, let me connect it and see. Positive probe on this point here. Yes, on the other resistor. Yes, there's a buzzer sound. You can see we have a buzzer sound on this point. Yes, we have a buzzer. And what else here? What about the second line, which is this one? It's going straight away to a weir here, so we can check it here. Yes, this is also, we have a continuity somewhere here. Yes, one point here. Yes, we have a continuity. Yes, so there's no problem with that. So it is just a corrosion on those tracks. So okay, no problem. Now let me connect the adapter and see whether we have any improvement. So let me try to trigger the power button and see whether the board is turning on. Okay. Okay, now the power supply is visible to you now. So now we can check with the power supply and see whether the board is turning on with the power button. Okay. Now it's connected. Now it is automatically turning on, no problem. Now let me press the power button and shut down the board. Okay. Now if you see, the ampere went to 10 milliamps. So if it is 10 milliamps, then the board is not going to turn on, I'm sure. So I'm going to press the power button and the board is not turning on. Yes, you can see the board is not turning on. Okay, fine. So let me connect the adapter and again disconnect. Let me disconnect the adapter and again connect it. Okay. Yes, the board is turning on again. Okay. Let me press the power button once. Yes. No, still it is going into 10 milliamps. So the board is not going to turn on. Alright, so there's a problem on the EC chip, or else still we have a problem on these lines here. So it looks like there were some components on these places, I think. I'm not sure with that. Maybe these pads are left open. Okay, let's check whether this is a ground point, just to make sure it is a resistor or capacitor or something else. So we need to find a clear board image in order to find is there any component on this place. So this is ground and this is also ground. It looks like a capacitor maybe. Yes, it looks like a capacitor. So if there's no capacitor in signal lines, so there won't be much problem. Okay. Continuity on this place. No continuity. Yes, continuity. Continuity is there. Yes, there. Yes, it's there. Yes, okay. What about this one here? Yes, continuity is there. No problem with that. So it looks like everything okay. Everything is okay, I think, actually. So there's a problem with the EC chip, I think. Okay, so for a good measure, I can just check the regulator of the 1.05 volt when the ampere reading is at 10 milliamps. Okay, so here we have the regulator for 1.05 volt. So we need to check the enable signal and also the power good output signal on this pin here when the ampere is stuck at 10 milliamps. So on that we can conclude whether we can bypass the signal with an always voltage and see whether the board is turning on properly. Okay, right. So first let me open the data sheet for this IC in order to see which pin is having the enable signal and which pin is having the power good output signal. Okay, and if this voltage is being produced before like an S4 and S3 signal, and the power good signal should be sent to EC chip, and once the EC chip receives the power good input signal to the EC chip only, then it will send other signals to the PCH and other important signal on its GPIO pins. So if there is no power good output on this regulator, then EC will not release other important signals. So on that case we might find a no power problem. So anyhow, we don't have a schematics for this motherboard, so we have only one chance is to open the data sheet of this IC and find which pin is receiving the enable signal and which pin is providing the power good output signal. Okay, so let me try to read the number of this IC. Yes, it's equal 5 equal 2C. Okay, let us try to search this number. Okay, finally got the data sheet, but the data sheet is scrambled here, so the letters are bigger, so we can't read actually. Anyhow, it is okay, we'll try our best. Okay, so now we can check on pin number 6 and 7 whether we have a voltage like 3.3 in order to enable the voltage uh, on the coil of this regulator. So actually this is a VTT regulator, which means a RAM regulator, but they are using this regulator to generate 1.1 volt or 1.05 volt in this motherboard. So in this motherboard there is a separate RAM regulator, so it is also the same as this one here. So they are using two same regulators for generating different voltages for different sections. One is for the RAM and one is for the PCH or SOC powering up voltage. Okay, so that is fine. So we need to take a note of pin number 6 and 7, actually 7 and 8. Yes, we need to check 7 and 8 whether we have enable signal when the ampere reading is at 10 milliamps, because at 10 milliamps only we are not getting an output on this regulator here. If we are having a low logic on this point, so we can say that there's a problem with the EC chip or maybe the BIOS inside the EC chip. So you can see the EC chip is a BGA technology on this motherboard, and it is an ENE production, ENE EC chip, and we can just program those EC chip. So as a cost effective way, what we can do is we can disconnect, we can separate these signals from the EC chip, and we can provide the other signal like always on 5 volt always on or 3 volt always on signal into this pin here. So once this IC receives the 3 volt or 5 volt always signal, then it will release the 1.05 volt in this motherboard. So at that time we might get a reading around 30 milliamps. So when the board is at 30 milliamps, so the board will be turning on. Okay, so this is the IC that produces 1.1 volt in this coil here. So this is the RAM regulator IC, so they are using this for just producing this 1.1 volt here. So as we looked into the schematics, so we can see on the data sheet we can see it's pin number 1, 2, 3, 4, 5, and 6, 7, 8, 9, and on pin number 10 here we have the power good output, and on pin number 7 and 8 we have the S3 and S5 signal. So we can just check only this signal here whether we have the enable 3.3 volt when the ampere is stuck at 10 milliamps, or in other words, if there is no power on the motherboard, if it is not turning on when we press the power button, let's check whether we have enable signal on this point. And if we don't have an enable signal, we are going to isolate this section by cutting this trace, and we are going to provide another 3.3 volt enable signal from an always state to this pin here, and make the regulator IC to generate this 1.1 volt, and see after that whether the board is turning on if we press the power button. And if the board is turning on, then we can win this case. Okay, now let me connect the adapter. Right, adapter connected, and the board has turned on. You can see the ampere reading is around 600 milliamps. So I'll just show you the readings here. All right, so first we can check on pin number. So we must be very careful. We should not short the enable signal with the nearby pin here, because that is the supply voltage for the chip, which has 18 volt in its input. All right, so let me check first on that pin whether we have enable signal. So now the board is turning on. You can see the ampere reading is 600. We have the enable signal, and the power good output also we have a voltage there, that is 1.5 volt. So 1.5 volt is okay. Let us check the diode value. Yes, we have 500. So 500 is the best reading, which shows it's a high logic, so there's no problem. Now we need to press the power button and turn off the motherboard and see the ampere reading. Okay, now it is stuck at 10 milliamps, and you can see now the diode reading went to 0.014, which means it's a low logic now. So the power good output is now at low. Okay, it's fluctuating, I think. Let me probe it again. Yes, it is 0.014. And if I go to the enable signal also, we have the low logic. So it is sending a low logic on the enable signal for this IC. And with respect to the enable signal is low, then it is the IC is sending a low logic on the power good output pin. So as I told you earlier, now we are going to isolate the enable signal from the EC chip, and then we are going to provide an external 3.3 volt enable signal, which is equal to the 3.3 volt or 5 volt coil voltage enable signal here, and see whether this IC is generating a voltage. Okay, right. So first we need to cut this trace here. I think we can remove this resistor from this place. Maybe it could be a 0 ohm resistor. Let me check that first. First of all, I will disconnect the adapter. Okay, let me see. Yes, it's 0 ohms resistor. So I can just remove this resistor and provide a 3.3 volt on this pin here. So it will be a best way rather than just cutting the trace. Fine. Okay, now the resistor is removed. Let me cool down the board a little bit. So here is the first pin of the resistor. You can see the EC chip is sending 90 ohms. Okay, and on this side we have high logic. Okay, we have a high logic. So if I touch this button, this pin here, the other side of the resistor, the ampere reading is around 110 milliamps, isn't it? Yes, you see 110 milliamps. So if I check the voltage now, so I'm not getting any voltage. Okay, fine. So let me check with this one. Yes, still we are having 100 milliamps. So I think the voltage is generated. Let me check here. Yes, so some voltage is being generated when we provide an enable signal on this point here. So let me try to provide a 3.3 volt voltage input on this line somewhere from the board. Okay, so now we need to find a 3.3 volt somewhere in this motherboard, which should be on always. Okay, now the ampere reading is at 24 milliamps, so it is better now, I think. Let me see. Okay, fine. Let me check the voltage. So it is better to find a nearby section where would be 3.3 volt. Okay. Yeah, we have a 3 volt on this point. So yeah, on both sides we have 3.2 volt. Okay, so on this point here we have a 3.2 volt, this point. So we can jump a wire on this point here and see that. Right, perfect. Right, let me connect the adapter. Yes, adapter is connected. Now the board is turning on. I'm going to press the power button. Watch out the display of the power supply. Okay, and now the ampere is at 18 milliamps. So now it is not at 10 milliamps, now it is at 18 milliamps. So if I press the power button, but the board is not turning on. Okay, but the ampere is at 18 milliamps, but the board is not turning on, isn't it? Yes. Okay, so I don't know what's happening here. The second time we are failing. No problem. Now let me check whether we have this 1.05 volt here. Yes, we have 1.05 volt, so that is present here. So the power good output signal, yes, that is also there. Power good output is also there. Okay, so what is actually happening here? So guys, do you know the actual problem in this motherboard? So I was just off the camera and finding some solutions for this problem and involved in research. So I was able to find a board view for this motherboard. So it was and it is very helpful for us to find the solutions for this motherboard. So only with the board view I was able to find the solution very quickly, and it's very easy. So if you look at the board view, so I was able to spot some components that was missing on the sections that we saw it was corroded, so which is on the back side of the SIO. So if you look here, we have only this capacitor, only this resistor on that place. We don't have this capacitor, this resistor, nothing is there. But it is not a problem if you don't have a capacitor or this resistor or this capacitor, even this resistor. But these two resistors are very crucial, because if you zoom it and find it, so you see it's lit switch and this is power switch. So these are the resistors that provide the pull-up voltage for each of these lines. So you see it's at 3.3 volt always line, and this is also 3.3 volt always line, and this provides the power for the the pull-up voltage for the lit switch, which is on the corner of this motherboard here. So if you take this lit switch, you can see on one side is connected to ground, on the other side is connected to VCC, and if you bring a magnet close to this Hall transistor, then it will conduct ground to this side. And if you don't bring a magnet close to this point, and this will be high logic. However, you need to give a pull-up voltage at this point in order for the EC chip to understand that there is no lit switch function in this motherboard. But as there was no pull-up resistor in this motherboard here, the EC chip was understanding that the EC chip is understanding that the motherboard is in a sleep mode. But the board is turning on if we connect the adapter even though we don't have these resistors. So why the board is turning on only once, but not after pressing the power button? So basically, if we disconnect the adapter, if we disconnect the battery, which is the main battery and the CMOS battery, the real-time clock inside the PCH and also the EC chip will be disabled, or it will be destroyed. So, and it will be reset to 0. So on that case, once if you connect the adapter, automatic power switch will be given to the PCH, and then it will release the S4 and S3 signals immediately. And also as the S4 and S3 signals are released, and the SIO will also send the S4 and S3 signals. And these pins, the lit switch voltage is also not there, but only once it will be okay. But if we shut down the motherboard, then it will sense this voltage. So these two resistors are crucial for in order to turn on the motherboard with by pressing the power button. So these two resistors are very crucial. So when the adapter is connected, so you can see when there is no battery or when there is no CMOS battery in the motherboard, and if you connect the adapter, all RTC sections, the real-time clock will be reset, and at that time the power button switch will be automatically triggered, and then it will send the S4 and S3 signals from the PCH, and as a result the board will be turning on. But if you press the power button and shut down the board, or if you shut down the board through the windows, then it will go into a shutdown state, and then the real-time clock will be active, and at this time these signal will be taken into consideration, and you should provide a 3 volt on this side and 3 volt on this side in order to make the board to turn on as a pull-up voltage. So if you don't have a voltage, then the EC chip will not understand that there is a signal generation on these two points. So you can see the value is 10k and this is 10k, and also here is also one resistor, but this is not much important. So it is AC in overcurrent hash. So this is also 10 kilo ohm. So anyway, we can place these three resistors in that place. So this is really an interesting case. So actually it's really an interesting case for me, guys. So it may be for you also, guys. So see the importance of lit switch and power switch pull up voltage in order for it to turn on. So it's very crucial. So now we are going to place these three resistors. Okay, right, so before replacing the resistors on that place, so it's here. So these are the two places, the three places, which is very important. So this line is for AC in overcurrent protection. This is the power switch and this is the lit switch. So these two resistors are very important. We need to replace this one. In addition to that, we can replace this also. So before replacing the resistor here, I wanted to check the voltage on these pins to see whether we have any voltage on that. So if you look at the power switch here, which is this one here, so if the board has turned on using the adapter automatically, if I press the power button, it is responding to the shutdown and it is going to shut down if I press the power button. But after, if I press the power button, it is not working. So even though there is no pull-up voltage on this pin here, the low logic is being recognized by the ECU chip when the power button is pressed after connecting the adapter. So this pull-up voltage is necessary in order to turn on the motherboard. So that's why the board is not turning on after it is shut down. So that's the important thing. And also what I'm going to do now, I'm going to replace the resistors one by one, and I'm going to check after replacing which resistor the board is turning on. So in that case, we can have a better understanding about the importance of that particular resistor in this place. Okay, so now let me connect the adapter and check the voltage on the power button here. So here we have a power button, so I can just check it. Let me turn off the board. Now it has turned on. Okay, fine. Now let me check the voltage on the power button. So here we have 2.2 volt. So actually we should have 3.2 volt. So we don't have a pull-up voltage. That's why we are having 2.2 volt at this pin here. And here we have the lit switch here on this pin. So this is the lit switch here. Hall transistor. You can see here this one. On this side here we have ground, no voltage. On this side here we have 3.3 volt, that is the supply voltage, and on the output side we should have 3.3 volt, but here we have only 2.2 volt, so the pulled up voltage is missing. So we can just place the resistor and come back and check whether we have the board turning on. Okay guys, so now I have replaced these resistors here. So 1, 2, 3, 4 resistors I have replaced, and every one are at 10 kilo ohms. So now I have just removed the resistors in the resistor in the lit switch line, and let's plug in the adapter and see whether the board is turning on, and then we can press the power button and try whether the response is there for the power button. So on that case, we can make a decision which signal is crucial for the board to sense the power button signal. Okay. Yes, the board is turning on. It is working fine. It is drawing around 600 and 700 milliamps. Yes. Now let me press the power button. Okay, the board has shut down. And if I press the power button, yes, now the board is working. So amazing. So now we have not placed the resistor for lit switch, but still the board is working fine. You see? So the important thing is the power button, power switch resistor is the important thing in this motherboard in order to respond to the power button signal. So if I check the voltage now after replacing the power button, power switch resistor there, the pull-up resistor, you can see we should have 3.3 volt. Yes, 3.2 volt. This is because we have a pull-up voltage on that line. Okay, and if I press the power button, yes, it is shutting down. And again, if I press the power button, yes, the power button signal is now responding. All right, so no problem. Okay, so the important point in this resistors here, this is the power button signal and this is the lead switch. So the power button signal is the important resistor in this place because it should be there for the board to sense the power button is being pressed or not. So if I remove this resistor now, the board should be in the previous condition. So now we have solved this motherboard only by just replacing this resistor here. So we have spent a lot of time to identify this component. So anyway, it was identifiable when we saw before, but we did not look closer, and after getting the board view we were able to find these components here. And then I will just go for a last test after connecting the display and see whether everything is working fine. Okay, right. So before that, I would like to check with the oscilloscope the timing sequence. So if you look at the ampere reading now, so I just wanted to tell you something. So I press the power button now. Yes, now the power button is pressed. So now the board is at standby, and if you look at the reading, it is at 10 milliamps. So this is the actual reading when the standby. So we saw 30 milliamps previously, but actually that is not. So due to some cases, so we can see there was some problem on this line here. Something is corroded and something there are some components missing here and there. So that could be a problem which brought 30 milliamps on the ampere reading. So now we have solved that one. So the particular ampere reading for this motherboard is 10 milliamps. So if I check the voltages, so we should see only 3.3 volt and 5 volt output. We should not get this voltage here. Yes, so previously we were reading 1.1 volt at this point. Now we don't have any voltage. And on this side, okay, yes, 5 volt and 3 volt. Yes, we don't have any voltage. So this comes during the run power stage, I think. So now it's a good measure point. So I will just press the power button and we can use the oscilloscope in order to identify at which timing this voltage is generated in the motherboard. Okay, we can check this with regard to ASUS signal from the PCH. Okay, so now I have connected the yellow channel on the 1.05 volt output, and the green channel I need to probe on the ASUS signal from the PCH. Okay, it's here. And look at the oscilloscope to see the time difference. Okay, let me set to single sequence function. Okay, and I'll just connect the adapter. Yes, so you can see now the yellow channel on top, it is generated first, and green channel, it is the second generated one. So the first channel is 1.05 volt and the second channel is ASUS signal, and we can see it is clear that ASUS signal is sent later, which is rising high later than the 1.05 volt output. So now I'm going to press the power button and shut down the board, and we can recheck again with pressing the power button and see whether there is a change. Okay, right, now I will press the power button. Okay, yes, now we have a slight difference in the reading. Wait a minute. Yes, it's here, and still we can see, so there's a difference in the signal timing. Still the 1.05 volt output is generated before the SUSC has signal from the PCH. Let me confirm it. Yes. So if we take the cursor function, okay, and yes, okay, the other signal, yes. So only after 19.8 milliseconds, the SUSC has signal is generated after 1.05 volt. So according to the timeline, we can see there's some discrepancies in the original original condition in this motherboard. So okay, anyhow, let it be. Now the board is working fine, no need to consider about this one. But if we have a problem, like if the enable signal for 1.05 volt is not present, or if the EC chip is not sending that enable signal, then we can just jump the enable signal from the always power states. So because you can see the 1.05 volt is generated before before the SUSC has signal from the PCH. So then it will be fine. But according to the timeline and the time sequence in the board image, so we can see that the SUSC has signal is coming before 1.05 volt, but here we have 1.05 volt first and the SUSC has signal at the second. So anyhow, we don't need to go deeper into this case, so we have already solved the motherboard, so let it be. Okay guys, so now we have assembled the motherboard inside the laptop. I'm going to connect the adapter, okay, and the board has turned on. Yes, we got the display. Yes, okay, it's shutting down. Still it is shutting down. Okay, now it has shut down. So the ampere reading is 13 milliamp. So this is the appropriate ampere reading during the standby for this motherboard. So let me press the power button, and yes, the board is turning on. So there's no problem. So by this video we have learned how the signal timing that comes so one after the other using the oscilloscope. So we can use this oscilloscope feature, which is the single secant function, in order to identify which signal comes first and second. Then we can make a decision on where is the problem is. So I think we have learned some new things today, so I hope it might help you guys. So anyhow, thanks for watching and stay tuned for our future updates. Okay.